Perfect. Good morning, everybody. See a lot of fresh faces. Great. My name is Thomas Weble. I'm co-founder and the CTO at Flex Optics, a company which is specialized in pluggable transceivers, especially the optical ones. And in my daily job, actually, I really work quite a lot with transceivers and the optical components there, but also in the counterpart, people are network engineers, and I help them to design and build optical networks. When I look a little bit backwards in history, looking at the networks we have built 10 years ago, I see a slightly change now. Also looking at yesterday's presentation, the complexity in the network itself got way bigger, or the network itself got way more complex. The same we can see also in optical transceivers. When we compare, let's say 10 years ago, 10 gigabit was somehow a new technology and starting to be implemented in the field. Now in these days, 100 gigabit becomes commodity, and 400 gigabit is the leading edge technology actually. So this talk covers, at the end of the day, the complexity of the transceivers itself, because in parallel, what we see in the network, that the complexity got up, the same happened to a transceiver. So what I brought there for you is a comparison of a 10 gig transceiver and a 400 gig transceiver. I opened them up for you. And on the top, this is an SFP plus, and below you see a QSFP DD. Opened up, removed the housing. I don't want to talk about a 10 gig any longer. So the talk mainly covers three components inside this transceiver. First of all, the transmitter and the receiver section, these tiny golden boxes, like here. And then this new introduced component, the DSP or digital signal processor. This is going to be at the end of the presentation. So let's start with the transmitter section to give a rough idea what's happening inside of that transmitter. So this golden box, when we open it up, it's first of all an empty golden box. And in the optical environment, this is also called a TOSA, a transmitter optical subassembly. And you will see now why it's a subassembly, because we have to fill that golden box with some components. For your imagination, this box has a dimension of 5 by 10 millimeters, so it's quite small. And we start with the electrical connector at the back, actually, which connects to the PCB of the transceiver itself. And that's where we fit in 4 lanes of high-speed signal for a 100 or 400 gigabit transceiver. At the end of the day, the TOSA looks pretty much the same. We have 4 lanes feeding into that TOSA, getting the high-speed signal on the electrical side. So first of all, for sure, we talk about optics. So first of all, we have to convert that electrical signal into an optical light level, and that's typically done with laser diodes. Pretty straightforward, everyone knows them. And those laser diodes have basically 2 interesting characteristics. First of all, they take current to operate, and this current is going to heat them up. Now, this current, at the end of the day, when they heat up, it has a side effect that the wavelength of the emitted light is going to drift a little bit when the temperature is changing. And that's something what we really want to avoid in optical engineering, actually. We want to keep the wavelength stabilized to a certain spot, because otherwise, when it's going to drift away, the laser is not in focus any longer, and then your transmission will fail. To do that, we use a cooler. This cooler, again, takes current to cool down or to keep the laser diode on a certain temperature, and with the result to have a stable wavelength. The second characteristic of that laser diode is the light which is emitted is, let's say, it's blurring out. It's not really focused, pretty much like people are wearing glasses. When they take off their glasses, they don't see properly. And the same applies to a laser. So like in real world on humans, we wear glasses. A laser needs also to wear glasses. We place there optical lenses. In total, we are talking about 4 lenses, because we have 4 lasers inside there, driving 4 electrical lanes of the high-speed signal. And to give you a rough idea about those optical lenses, the size is in XYZ, it's around 0.5 millimeters, so they're pretty small. And in production phase, these lenses need to first of all be placed in XYZ to be in focus to the laser itself, that we get a proper signal. This is done in 50 nanometer steps, to move it and wobbling around in 50 nanometer steps. And then we have to fix it there. And that's another big challenge. Actually, this is typically done with UV hardening glue. Now you can imagine, first of all, this glue needs some certain characteristics, especially when it comes to the lifetime of a transceiver. It'll last for at least 5 or 10 years, so this glue needs to keep its consistency for the 5 or 10 years and can't change its behavior also over the operating temperature range of the transceiver itself. And if it would do so, the lenses would shift and then the laser would be out of focus again. So this is quite a little bit chemistry is also involved there to have the right glue for that application. So what we have now is we have focused light coming out of those 4 lenses, but actually they would hit the wall here, but we need to insert them into the receptacle. This is the typical receptacle for a LC plug, and now you can also see the dimensions. That's the receptacle where you plug in the LC plug, and it's quite big here on the screen, but when you see it in the real field, it's a tiny part. To combine all the 4 wavelengths, this is done with an optical multiplexer, and some of you might be familiar with an optical multiplexer. You know them as a 1U chassis thingy, having 8 or 16 channel in CWDM or 20 or 40 channel in DWDM. Now here, in this situation, we have a 4 channel CWDM or LAN WDM max, which combines all the 4 wavelengths together, that they're gonna be inserted into the receptacle. How does this max work? It's filter block, and it's pretty much physics from high school. So it's based on the principle of a mirror, and this is an angled mirror, so the light is inserted into that filter block, and this surface there is dotted. It's dotted glass, and it's also a little bit, it has an angle. So the light is reflected, pretty much like when you take a ball and throw it against the wall, it's going to bounce back. The same happens with light here as well, or when you look in the morning into the mirror, you most probably see a proper face. The same happens inside this mux. So the light is bouncing back and forward, and at each step a new wavelength is adding to that light path, and then at this certain spot down here it's going to be released into the receptacle. So now we are on the fiber, on the couple of kilometers or more than 100 kilometers, doesn't matter, and then on the other side we hit the receiver. The receiver, again, it's not a golden box now, it's a gray box, but it doesn't matter. It's an empty one again. And what is inside in the receiver? So first of all, yes, the light is coming into the receptacle, into that this gray box, and now we have to separate all the 4 wavelengths again. This is typically done with a demultiplexer. It works the other way around, like the multiplexer. It separates all the 4 wavelengths, beside the fact that we do have a filter block here, which only allows the green light to pass, and the other colors are going to be bounced back and forward until they hit the appropriate filter up to the yellow one down here, and we have separated all the 4 wavelengths again. And then we need again optical lenses the other way around, like on the laser side, to get the light coming out of the filter block, which is not focused properly, need to be focused, to hit a pin diode. This diode does the other way around compared to the laser diode. It converts the optical light level to electrical level. Now, the electrical level coming out of that pin diode has a really low amplitude, and post-processing systems like the ASIC or DSP, they can't handle that signal at all. So, like you do at home when you listen to music and it's too quiet, or the music isn't loud enough, you boost up the amplifier and it's louder. The same is done in a receiver in the ROSA. We place there an amplifier which boosts up the amplitude coming out of the pin diode. One side story here maybe, when you have in the field had the experience running a transceiver which is capable to do 80 kilometers, like an SFP plus ZR. They do have a really sensitive receiver, and some of you might have got that experience when they connected a ZR transceiver back to back with another 80 kilometer transceiver without any attenuation. The link came up, it stayed there for 5 seconds, and then it dropped, and it never came back up again. Actually, and then people say, well, you have burned the receiver. Yes and no. What you actually have burned is the amplifier, and the amplifier destroyed himself because on the input side, the amplifier got way too much current because the light level was too high, and then it destroyed himself. So if you have the chance and you have to destroy your ZR transceiver, open up the ROSA, replace the amplifier, and it will do its job again afterwards. So that's the thing about burning the receiver there. Okay. So we covered now the transmitter and the receiver section of that entire setup of a transceiver. When it comes to production, this could be a very long talk, so I don't want to get too much into details of the production, but I think for network engineers there is an interesting thing to know is, and I want to point out on the production side, on the testing side, when we produce an optical transceiver, and especially about the timing, how much time does it take to produce a transceiver and also to test it. I took real figures out of production, and I explained that graph a little bit. So on the x-axis, we do have the 3 generations of 10 gig, 100, and 400 gig transceivers. And on the y-axis, it's timing in minutes. I do have 3 graphs here. The blue one is the assembly of the overall transceiver itself. To give you a rough idea, a 10 gigabit transceiver to assemble and to test in combination is roughly 8 minutes. Yes, for sure, we do this in batches, also later on at the testing, but it's roughly 8 minutes. Now the green line, and that's the interesting one, which has a really steep rise up here, is the testing. And the testing, and the orange one is the combination of both of them, or the overall time. So what we see here, the 10 gigabit assembly and testing, as I said, roughly 8 minutes. But when it comes to 400 gigabit, we are talking about assembly of roughly 25 minutes to build the entire TOSA, ROSA, assemble it to a PCB, and then and mount it. But when we want to test the whole beast, this takes roughly 90 minutes. So this is a major difference. Now you can imagine if you are in production environment and you want to save costs, you don't do this on assembly, you do this on testing. Because also in testing, there is very expensive equipment involved to test a transceiver. And also when you occupy that equipment for a long time, like those 90 minutes here, you can do the math. You can't do that many of transceivers a day while you're occupying your equipment. And there are actually 2 ways to handle that. There's a bad way just to get rid of test cases. And for sure, when you get rid of test cases, then you get down the overall testing time. Or, and that's something what we also see in the DevOps environment, in network engineering, you do automated tests. And the same happens in the optical engineering environment as well. So when you automate your test cases, you get down the overall timing at the end of the day, and that's where you save time on testing and time on the production. This really matters. To give you an idea about a test case, I took the example of temperature tests. So here I do have the temperature test at 0 degrees centigrade and also on 70 degrees centigrade, and we see, well, the green laser here, when we change the temperature, it's going to be drifting away a little bit, but at a certain time it will stabilize. We could say, well, okay, it passed the test. But if we take a second constraint into that test, which is the time, and we say, for example, okay, we start at 0 degrees centigrade, keep the laser there for not longer than 10 seconds, and within 10 seconds it needs to be stabilized, and then boost up the temperature to 70 degrees within 60 seconds, and again give the transmitter, for example, to stabilize the laser within 10 seconds. The same part might fail now because the green laser, it took way longer to get stabilized, and there might be something broken inside or maybe not working properly, and this might end up in the field later on in a faulty part. And so there you can see how you define the test cases. You get either a pass, or later on you get a fail. So the definition of the test case really matters here. So So the overall goal for sure is coming out of production is getting the green traffic light saying, well, okay, we got a proper tested part. So far, we covered now the overall transceiver, the transmitter section, receiver section. And as at the beginning I said, there is this new introduced digital signal processor for 400 gigabit transceivers. And I want to point out one certain function of that DSP. Generally, it has two functions. The one is taking care about the encoding. Typically, it's PAM4 encoding, but that's something I don't want to cover now. And secondly, it's the forward error correction. What is the forward error correction? And maybe if we do a little bit looking back in history, we already know error detection. When you look in your Ethernet frame, you have the 1,500 bytes, the frame. At the end, you have the cycling redundancy checksum of 4 bytes. This is actually error detection. So with those 4 bytes, you can detect an error, but you can't correct it. Now, with higher speeds, there is the demand also. Yes, there are errors, and it is not sufficient any longer just to detect them. We also need to correct them, and that's where the forward error correction takes place, and it's done in the DSP. A little bit of recap on 100 gigabit. Forward error correction was first introduced in 100 gigabit, but not on the transceiver side. It was introduced in the switching and routing side. And so basically, how does it work? We have a FEC encoder on the switch, and it encodes our stream, brings it on the line via the transceiver, and then on the other side is a decoder. How does this in principle work? I took an artificial example here with a lorry and a truck to explain a little bit. On the first step, the lorry is our FEC encoder, and the bricks on the lorry itself, this is our payload. And then when the lorry hits the dodgy road, which is our fiber, all the bricks inside there get somehow disordered. Even one brick is falling off. Actually, this doesn't happen in the optical environment, but and then the third step, the excavator, this is our FEC decoder. So what does the excavator do? It brings all the bricks on the lorry back in order that the post-processing workers can do something with those bricks, and that's the same happens with the FEC decoder there. Now you can imagine that this excavator takes a little bit of time to get all the bricks back in order and sort them, and also FEC needs time to operate. So in total you get an additional delay of around 100 nanoseconds on your 100 gigabit link when you enable the FEC there. That's something to bear in mind. So you need to give the FEC a little bit time to operate. How will it look in 400 gigabit? It will get way more complex. Instead of having only the FEC on the switching side, like here in the decoder here, we also have FEC involved in the transceiver itself inside of the DSP. So first of all, the FEC, I call it here FEC2, encodes the signal, and then the transceiver FEC will decode it, and then the transceiver FEC again encodes it, brings it on the fiber itself, and on the other side it happens the vice versa. So the FEC1 decodes, and FEC2 encodes it, brings it over to the FEC2 decoder, and then post-processing systems like the ASICs and so on take over of the payload. And there are pretty much two findings where I think it's important to mention. The first one is about the FEC. You might have discovered issues on a 100 gigabit link, when you established the link and you had bit errors on your line. So the first thing you need to double check is the FEC enabled or disabled, because depending on the type of application you're running there, it's either intended to be enabled by default or disable the FEC. So an example is like a 100 gigabit SR4 doing a multimode transmission up to 150 meters. The FEC needs to be enabled by default just on the fact that it's multimode. And the SR4 technology there. So typically the switch operating system, when it gets the transceiver plugged in, it recognizes it will enable the FEC. But in some circumstances it can happen that it doesn't enable it, so you better check if the FEC is enabled on both ends if you're seeing bit errors. The second one is, you might also have experienced, okay, the link doesn't come up at all, and then you also need to check on both sides actually, is the FEC enabled, because we have seen scenarios that the left switch, for example, enabled the FEC, And the right switch didn't do it because it was a different vendor, different operating system, and a different implementation at the end of the day, so it didn't automatically enable or disable it. So there was an unequal amount of facts involved. And for sure, when you have an unequal amount of facts, it won't work at all. So you always need to make sure that you have the same amount of facts involved. And in 400 gigabit, it's not only 0, not only 2, it can also be 4. So you need to make really sure which fact is involved, which is enabled, the transceiver one or the one on the switch, and this on both sides. That's the tricky part here. Let's see how the operating systems of the switches will handle this in the future, also that you can differentiate which fact is enabled and which is disabled. This brings me to a small summary. Also a small outview what will happen in 2020 in the optical networking. For sure, 400 gigabit is a hot topic, but like people expect, like LR4 is not standardized yet. There are still ongoing discussions if it will be from the wavelength grid, if it will be CWDM4, which has a spacing of each laser of 20 nanometers, or is it going to be the LAN WDM spacing with 5 nanometer, which we know from 100 gigabit LR4, which is standardized for a while. But for the 400 gigabit, this is still not defined yet. There are different tensions in industry to push to CWDM4, because if you have a broader spectrum, it's way cheaper to produce. But also there are advantages if you go to the LAN WDM. So we will see it in 2020 where standardization, especially IEEE, will make their decision. And also from the real LR4 application, like doing single mode transmission up to 10 kilometers, which we are used, or which we know from 100 gigabit or even 40 or 10 gigabit, doesn't matter. There are ideas to go down to 6 kilometers and so on. Let's see what will happen in 2020s. The second one is, I didn't expect it actually, to be honest, is I thought the train for 100 gigabit is over. No one is spending any money on the development of 100 gigabit, but we have seen latest development in 2019 and also ready products on a real ER4 doing real 40 kilometers transmission on a single pair of fiber, and or even like a ZR4 doing 80 kilometers with a 100 gigabit transceiver. And I'm talking here about the interesting form factors like QSFP28 and not taking the CFPX family in consideration here. And the third one is the 400 gigabit DR4. It's mainly the DR4 is a data center application up to 500 meters. The specialty, what I think, which will come out this year, is with the SN plug. What is so special about the SN plug? Quite of you know, since the introduction of 40 gigabit transceivers, the MPO plug or MTP plug from US Connect, it was this multi-fiber push-on plug with 8 or 12 fibers in one plug, which you plugged in and out, which is technology-wise a great plug, but maintenance-wise horrible. The problem with this typical breakout mode is you have those 8 fibers aligned next to each other, combined in one house, and you plug it into the transceiver, and then you can do this fan-out mode to 4 times 10 gigabit or 4 times 25 gigabit, which is great. If you want to maintain one single link, you have to unplug the entire plug, so all the other 3 links will drop. With the SN plug, this issue is solved. So the SN plug itself is a single plug with holding 2 ferrules. In combination with its counterparts, it's going to be a cluster. So it's a block of 4 plugs combined into the receptacle of a QSFP DR4. And if you want to maintain a single link, you can just release two ferrules, and the other 6 ferrules will stay in the transceiver. Why is this so important, or why is it so interesting? With 400 gigabit, it's not only a pure 400 gigabit transceiver. You can also imagine of applications doing out of a 400 gigabit transceiver driving 4 times 100 gigabit. You could either do, for example, a full mesh. So you have, for example, 3 routers. Each of them is holding a single 400 gigabit transceiver. So you could connect from router A to B with 100 gigabit with one transceiver. And then from the same transceiver, you could do 200 gigabit and 2 times 100 gigabit to router C. And then from router C to router A, you could do 100 gigabit again, and you only, let's say there are only 3 transceivers involved. So you can do a really nice mesh. just due to the fact that you have the receptacle of the SN plug there. Coming from the DR4, also new things happening on 100 gigabit LR. And why do I mention 100 gigabit LR here? This is the section when it comes to single lambda transceivers. So there will be new 100 gigabit transceivers coming out, but this is not an LR4, which we are used to use in these days. No, this is an LR1. So it has one lambda out of the QSFP28 driving 100 gigabit. And when you look back to the 400 gig DR4, this is the perfect counterpart to connect either a 400 gigabit DR4 to a 400 gigabit DR4 for sure, or doing the breakout mode in terms of 4 times 100 gigabit. And then if you have the counterpart interface there, is a 100 gigabit LR connecting to a DR4, for example. This would be doable. When we go to the lower speeds, but also the DWDM grid, 40 gig and 25 gig DWDM is available straight out of the transceivers up to a power budget of 11 dB, so no external amplification is needed there. I'm really only focusing on the pluggables itself without any external amplification, etc. This, to summarize it, brings me almost to the end of my presentation. For us itself, especially the DSP and the 400 gigabit transceivers will give a new challenge, also when it comes to the implementation of the Flexbox, how we change the behavior of a transceiver. So far we are familiar with the microcontroller inside of a transceiver, and now with the 400 gigabit this will be a little bit game changing, because also the DSP is running a firmware, is running a configuration, and needs to be tweaked and optimized. Brings me to the end. If there are questions, I'm happy to take them. Thank you very much for listening.
Hello. I have a question. For 400 gig, when you mentioned that there's like almost 4 different FECs running on a link, how much is the latency increased with those FEC working? Do you know?
Yeah, so it will double. So you will be roughly at 200 nanoseconds 200. If you have both FECs at each side involved. Yeah, switch FEC, transceiver FEC on the left side, and switch FEC and transceiver FEC on the right side.
So total will be like 200 milliseconds.
Yeah. Okay. It will depend also on the implement. So the 100 nanoseconds is a rule of thumb, roughly. It depends on the type of FEC. There are different type of FECs out there, also proprietary ones, and then standardized ones from the IEEE. But it's roughly around 100 nanoseconds. There can be some of them doing only 70 nanoseconds, but it's roughly in that range.
Okay. Yep. Thank you.
Welcome.
Hey. Juuso Lehtinen here.
Sorry.
Arista Networks. A question about testing. You mentioned that testing times have been going up exponentially. 10 gig was 3 minutes, 100 gig 30 minutes, and now 400 gig 90 minutes. Is it just because 400 gig is the latest technology that testing time is so high? Are you expecting that to go down from the current 90 minutes to something like 30 minutes or even less than 10 minutes in the future?
That's a really good question and really hard to answer. From the point of testing equipment, I wouldn't see it getting down, because the equipment is, yes, it's expensive, but it's still capable to handle it. The problem at 400 gigabit is mainly the temperature. So you need to give the transceiver a little bit time anyway. Plus, I think automation can bring the timing down in terms when you, that's what I think. But it's difficult to answer. Sorry.
Thank you.
All right.